Welcome back to the channel. Today, we're diving deep into one of the most powerful yet underrated architectures in deep learning, the Gated Recurrent Unit, or GRU. If you've ever wondered how your phone predicts your next word, how Google Translate works so well, or how chatbots understand context from previous messages, you're looking at the magic of recurrent neural networks. And GRUs are one of the best implementations of this concept. This is AI Academy, and by the end of this video, you'll not only understand what GRUs are, but you'll also know exactly when and how to use them in your own projects. So, let's get started. Before we jump into GRUs, let's understand the problem they solve. Imagine you're reading this sentence right now. Traditional neural networks process each word independently. They have no memory of what came before. It's like having amnesia after every single word. But human language has context. The meaning of bank is completely different in riverbank versus money bank. We need our neural networks to remember previous words to understand current ones. This is where recurrent neural networks come in. But vanilla RNNs have a critical problem called the vanishing gradient problem. As information travels through many time steps, it literally vanishes. It's like playing telephone. The message gets corrupted. RNNs struggle to remember information from more than a few steps back. Enter GRUs. They solve this memory problem elegantly and efficiently. A gated recurrent unit, or GRU, is a type of recurrent neural network that uses gates to control the flow of information. Think of gates like smart filters. Just like you might use a filter to keep good coffee grounds and remove the bad ones, GRU gates decide what information to keep, what to forget, and what to pass forward. GRUs were introduced by Kyung-Hyun Cho and his team in 2014 as a simpler alternative to LSTMs. They have fewer parameters, train faster, and often perform just as well. The key insight is this. Instead of having separate memory cells like LSTMs, GRUs combine the hidden state and memory into one unified state. This makes them more efficient while maintaining the power to capture long-term dependencies. Now, let's look inside a GRU cell. Every GRU has two main gates, the reset gate and the update gate. The reset gate decides how much of the previous hidden state to forget. Think of it as a forget button that can be pressed partially or fully. When the reset gate outputs 0, it completely forgets the past. When it outputs 1, it remembers everything. Usually, it's somewhere in between. The update gate decides how much of the new information to use and how much of the old information to keep. It's like a mixing dial on a sound mixer. Here's the brilliant part. These gates work together. The reset gate creates a candidate for new information, and the update gate decides how much of this candidate to actually use. Let me show you this with a simple example. Imagine processing the sentence, "The cat sat on the mat." It was comfortable. When processing it, the reset gate helps focus on recent relevant information, while the update gate decides how much to incorporate the new context about comfort. Don't worry, I'm going to break down these equations in the simplest way possible. No scary math here. Reset gate. RT equals sigma of WR times HT minus 1, comma, XT plus BR. This just means look at the previous hidden state and current input, multiply by some weights, add bias, and squash it between 0 and 1 using sigmoid. Update gate. ZT equals sigma of WZ times HT minus 1 plus XT plus BZ. Same idea, combined previous state and current input to get a value between 0 and 1. Candidate hidden state. H tilde T equals tan of WH times RT times HT minus 1, comma, XT plus BH. Here's where the reset gate kicks in. We multiply the reset gate with the previous hidden state. This is the selective forgetting in action. Final hidden state. HT equals 1 minus ZT times HT minus 1 plus ZT times H tilde T. And here's the magic. The update gate decides the final mix. It's like saying, take some of the old state and some of the new candidate and mix them based on the update gate values. That's it. 4 simple equations that create powerful memory capabilities. Now, let's compare GRUs with their famous cousin, LSTMs. This is probably the most common question I get. LSTMs have 3 gates: input, forget, and output gates, plus a separate cell state. GRUs simplify this to just 2 gates and combine hidden and cell states. Parameter count. GRUs have about 25% fewer parameters than LSTMs. This means faster training and less chance of overfitting on smaller datasets. Performance. In most tasks, GRUs and LSTMs perform similarly. Sometimes GRUs win, sometimes LSTMs do. The difference is usually small. Training speed. GRUs typically train 15 to 30% faster due to their simpler architecture. Memory usage. GRUs use less memory during training and inference. When to use which? Use GRUs when you want faster training and have limited computational resources. Use LSTMs when you have complex, long sequences and plenty of computational power. Let's implement a GRU from scratch using PyTorch. I'll show you both the theory and the code. First, let's create a simple GRU for text classification, predicting movie review sentiment. Here's what's happening. We embed our words, pass them through the GRU, and use the final hidden state for classification. Let's also look at a more advanced example, using GRU for sequence-to-sequence translation. The beauty of GRUs is in their simplicity. Just a few lines of code give you powerful sequence modeling capabilities. GRUs are everywhere in modern AI. Let me show you some amazing applications. Language modeling and text generation. GRUs power many text generation systems. They can write stories, complete sentences, and even generate code. Machine translation. Google Translate and similar services use GRU-based architectures to understand context across languages. Speech recognition. GRUs help convert your speech to text by understanding temporal patterns in audio. Time series prediction. From stock prices to weather forecasting, GRUs excel at finding patterns in sequential data. Sentiment analysis. Understanding the emotional tone of text by considering word sequences and context. Music generation. AI composers use GRUs to generate melodies that follow musical patterns. The common thread? All these applications involve sequential data where context and memory matter. Let's be honest about GRUs. They're powerful, but they're not perfect. Advantages: simpler than LSTMs. Fewer parameters mean easier training and less overfitting risk. Computational efficiency. Faster training and inference compared to LSTMs. Good performance. Often matches LSTM performance with less complexity. Gradient flow. Better than vanilla RNNs at handling long sequences. Limitations. Not always the best. For very long sequences, LSTMs might still have an edge. Limited expressiveness. The simplified architecture might miss some complex patterns. Data dependent. Performance varies significantly based on your specific data. Modern competition. Transformers have largely replaced RNNs for many NLP tasks. And that's GRUs in a nutshell. Let's quickly recap what we've learned today. GRUs are a powerful, efficient alternative to LSTMs for sequence modeling. They use two gates to control information flow, have fewer parameters, and train faster while maintaining excellent performance. Key takeaways? Use GRUs when you need efficient sequence modeling, have limited computational resources, or are working with moderately long sequences. Your homework? Try implementing a GRU for your own sequence modeling task. Start simple, maybe predict the next word in a sentence or classify text sentiment. If this video helped you understand GRUs, smash that like button and subscribe for more deep learn content. Drop a comment below with your GRU projects. I love seeing what you build. Next, we will be diving into transformers and attention mechanisms, the architecture that's revolutionizing AI. You won't want to miss it. Until then, keep learning, keep building, and I'll see you in the next one.